Hello students. This lecture is aimed as a basic introduction to the idea of quantum bits or qubits and how to compute with qubits. Through this lecture, we hope to show you some simple applications of the concepts that you've been learning over the last few weeks, namely linear vector spaces, the postulates of quantum mechanics, the idea of measurement in quantum theory, and of course the uncertainty principle. You can think of this as a fun extra lecture where you get to see all these ideas in action through a very current topic, namely that of quantum computing. Okay, so let's start with something that we already know. We're all familiar with the idea that classical information that we are used to, is stored in bits, right? Is stored in classical bits. And what is a classical bit? It's basically a binary valued object, one that takes one of two values, 0 or 1. Mathematically or formally, you would say that the classical bit is an element of a binary field. What about a quantum bit or a qubit? A qubit is essentially a two-level quantum system. Therefore, the state of a qubit is a vector in a two-dimensional complex linear vector space. You've already seen in your earlier lectures that such a space is typically denoted as C2, and the state of a qubit is any vector in a two-dimensional complex linear vector space. Now you know that if you want to construct a basis for C2, it's going to have two orthogonal vectors. You can normalize them. So essentially a basis for C2 will have a pair of orthonormal vectors. Let us choose to label these two vectors as ket0 and ket1. The reason we choose a 0, 1 label is of course to make an analogy with the classical bit values of 0 and 1. So ket0 will be the qubit state corresponding to a logical 0 and ket1 will be the qubit state corresponding to a logical 1. But now, unlike a classical bit which can only take either 0 or 1, only one of two values, the quantum bit can exist in any complex linear combination of 0 and 1. That's what I mean by the statement that ket psi, which denotes an arbitrary qubit state, lives in the span of 0 and 1. The state of a quantum qubit can be any valid linear superposition of 0 and 1. And so you already see a departure from the nature of classical information as you start thinking about information in quantum states. Do we know of any physical examples of such two-level quantum systems? Well, yes, we've already seen two physical examples of qubits in this course. The first one being the polarization states of light. Recall that if you have an EM wave propagating in, say, the y direction, then it can exist in one of two polarization states, namely the Z polarization or the X polarization, or of course it can exist in any linear superposition of Z and X. So if I denote my Z polarization state as a ket0 and my X polarization state as a ket1, then you've already seen that this is a pair of orthogonal states. They span a complex linear vector space, a two-dimensional complex linear vector space. So this is a valid realization of a qubit. Commonly, the Z is often called the vertical polarization and the X is often referred to as the horizontal polarization. The polarization qubit was one of the earliest realizations of a qubit, and till today this is the most preferred implementation for quantum communication purposes. The other physical realization of a qubit that you've already seen is that of a spin qubit. Recall that for spin half particles, the spin angular momentum can take one of two values in any direction, that's plus half or minus half. For the rest of this lecture, we'll focus on the spin Z observable, the sigma Z or the Sz. Recall that sigma Z or Sz are 2 by 2 matrices, and they essentially differ from each other by just a factor of h bar. So I'm going to use these two sort of interchangeably. The sigma Z or the Sz operator has two eigenvalues, plus half corresponding to plus half and minus half, correspondingly two eigenstates, which we denote as Sz plus for the plus half eigenstate and Sz minus for the minus half eigenstate. Recall that this is a pair of orthogonal states. You can normalize them. So you can associate the logical 0 with the Sz plus and the logical one with the Sz minus. And here you have another physical realization of a qubit. Once again, nuclear spins were one of the early implementations of quantum bits, and one of the early prototypes of a quantum computer was built using an NMR setup. Just to make things a bit more concrete from this abstract bracket notation, you can also write down a matrix representation. Recall that for the vector space C2, you can either associate a row vector representation or a column vector representation. Here I choose a column vector representation, and I say that my ket 0 is the column vector 1 0 and my ket 1 is the column vector 0 1. Of course, you know through the homework problems and through the lectures how to do an inner product in this case, and how to check now that these two states are indeed orthogonal. You can check that this inner product is 0, and you can also check that the norm is 1, that inner product of 0 with itself is 1, inner product of 1 with itself is 1. So this is a valid matrix representation of a pair of orthonormal vectors in C2, and this is one concrete way to represent the basis of a qubit space. Let's focus a bit more on this representation of qubits, and in particular I'd like to show you a nice geometric visualization of the state of a qubit. So I'm going to first make a slight modification to what I mentioned in the last slide. I'm going to demand that the state of a qubit be normalized. So I'm going to say that an arbitrary qubit state is a normalized complex linear combination or a complex linear superposition of the form A0 plus B1. And because it's normalized, I put a hat on the side, and I also now put in the constraint that mod A squared plus mod B squared should be 1, right? That's what I mean by a normalized state. Recall that the norm of this state is this mod A squared plus mod B squared, and I always set it to 1, right? So now the question is, how many real parameters do we need to describe an arbitrary qubit state? Well, we need 2 complex coefficients, right? And 2 complex coefficients would imply 4 real parameters. But now I'm going to claim that you need only 2 real parameters to describe the state of a qubit. First of all, note that from 4 we already come down to 3, right? Because you have this constraint, so 4 already becomes 3 because of this constraint of normalization, right? But how do we reduce that to 2? Well, there is one additional degree of freedom which actually is not a physical observable, and we'll see what that is. So first of all, let's use this normalization to make the association that the amplitude of A and the amplitude of B can be represented using a cosine and a sine. So I write the complex number A in terms of its phase and amplitude, B in terms of a phase and amplitude. Then because mod A squared plus mod B squared is 1, the amplitude of A can be a cosine and amplitude of B can be a sine. I have chosen to write this as a half angle, theta by 2. I could equally well have written just theta, but I choose theta by 2 so as to get a nice geometric picture, and this becomes clear as we go along. Now let's use this parameterization in this expression here and see what we get. So now your normalized state or your qubit state becomes e to the I alpha cos theta by 2 0 plus e to the I beta sin theta by 2 1. I can take this phase factor e to the I alpha out. So I just have cos theta by 2 0 plus e to the I phi sin theta by 2 1, where phi now represents the difference between beta and alpha. So phi here represents what I call a relative phase, right? So I have essentially taken these two phases which I have associated with the individual complex coefficients, and I have re-expressed it now as an overall phase and a relative phase, right? This overall phase, as was noted in an earlier lecture, is not a observable quantity, right? So I might as well just ignore this real parameter, because the state of a quantum system can only be described up to an overall phase. The state of a qubit can only be described up to an overall phase. So this real parameter alpha, which describes the overall phase, is not useful to us. What really matters is only the relative phase. So now you see I have described the qubit state using just two real parameters, two angles actually, theta and phi. One angle theta which represents the amplitude part, and the other angle phi which gives me the phase information. Theta goes from 0 to pi and phi goes from 0 to 2 pi, and this is now a unique representation of a qubit state. Because I have a half angle here, theta should go from 0 to pi so as to cover all possible amplitudes, and phi should go from 0 to 2 pi to cover all possible phases. Now if you look at this parameterization, you have two angles theta phi going from 0 to pi and 0 to 2 pi respectively. What geometric picture does this present to you? Well, you should be reminded now of a sphere, right? Because this should remind you of spherical polar coordinates with the r, let's say, being set to 1, right? So essentially, varying over theta and phi like this is like sampling the surface of a sphere, right? And so what we now have is a unique mapping from states of a qubit to points on the surface of a unit sphere in R3. And this is a very familiar object to us, and so now we can start identifying different qubit states on this sphere. This unit sphere is what is called a Bloch sphere, right? And I have this picture out here. This should be called the Bloch-Poincare sphere, often just referred to as the Bloch sphere. So now, where are the different states that we already have seen through this course? So first let's mark out the states 0 and 1, right? First of all, note this, that if I pick some arbitrary point here on the surface of the sphere, then theta is this angle, right? You can, so I'm sort of thinking of this as my z-axis, right? Then theta is this angle made with the z-axis, and when I take a projection down to the xy plane, the angle that it makes with here is the phi, right? Okay, so actually this is the angle that I want to say is phi, right? Okay, I'll just fix this error in the slides. Alright, so now where are the states ket 0 and ket 1? Well, when theta is 0, you are on the, essentially at the north pole, right? You are at the point where the z-axis intersects the surface of this unit sphere. So of course that is the state at the top out here is obviously the state ket 0, and when theta is pi, you can see that the state you get is ket 1. And of course recall that ket 0 and ket 1 for us are the eigenstates of the sigma z or the Sz operator. We have also written down the eigenstates of the Sx and the Sy operator. So let's try to identify those points on the sphere now. So the eigenstates of Sx, the plus half minus half eigenstates, remember, are of the form 0 plus minus 1 by root 2. So what kind of theta would give me a 1 over root 2 amplitude? Well, theta should be pi by 2. When theta is pi by 2, that brings us to the xy plane, right? And on the xy plane, when phi is 0, I get the Sx plus state. When phi is pi, I get the Sx minus state, right? Because phi is 0 means a 0 plus 1 by root 2, and phi is pi, remember the relative phase is e to the I phi. So when phi is pi, I get 0 minus 1 by root 2. What about the Sy plus minus half eigenstates? Well, they differ from this by this complex, by this factor I out here. So then all I need to do is use phi is equal to pi by 2 and phi is equal to 3 pi by 2. Okay, so I hope you check this out for yourself, and it's a useful exercise to see how you can use this theta phi parameterization to actually identify these three sets of states, these three sets of eigenstates on the surface of the Bloch sphere. Of course, the main takeaway from this is classically you would just have two states, right? Classically, a classical bit in this entire picture would just correspond to 2 points. Let's say, for example, the point corresponding to the ket 0 and the point corresponding to the ket 1. That is the north and the south poles of the sphere. But a quantum bit has access to all points on the surface of the sphere. The state of a quantum bit can explore the entire surface of the sphere, and that's an infinity of states that this quantum bit can explore, as against the classical bit, which can only be in one of these two states, 0 or 1. And it is this idea that gives rise to the so-called power of the quantum bit. The fact that it can exist in an arbitrary superposition allows it to explore a much richer variety of states compared to what a classical bit can explore. But how do we make the quantum bit explore these states? How do we transform, let's say, from a ket 0 to a ket 1? Or how do we go from a ket 0 to an sx plus? How do we go from a ket 0 to an sy plus? Right? How do we transform quantum states? Well, you need quantum gates, just like how you had classical gates, right? So remember, the classical logic gates are just Boolean operations. They are functions that map from bits to bits, right? And the simplest example you can think of is a single bit gate, namely the NOT gate. And what does the NOT gate do? It flips the bit. It changes 0 to 1 and 1 to 0. So let's try to write down the quantum version of this. Let's try to write down a quantum NOT gate. What should a quantum NOT gate do? It should map ket 0 to ket 1 and ket 1 to ket 0. What kind of object would do this? Remember, 0 and 1 are column vectors in our representation. And so if you use this column vector representation, then it becomes clear that the NOT gate must be a matrix. The quantum NOT gate must be a matrix which, when acting on 1 0, takes it to 0 1, and acting on 0 1 takes it to 1 0. And it's easy to check that this matrix is in fact a matrix that you've already seen. It's an off-diagonal matrix 0 1 1 0, and this is in fact the sigma x matrix which you've already seen in the earlier lectures. So this is how you would represent that in a circuit. I have an arbitrary qubit state coming in, which is some superposition of 0 and 1, and then I have the gate sigma x acting on it. This is the input, and the arrow of time goes like this. This is the output. The sigma x flips the 0 to a 1. It flips the ket 1 to a ket 0, and so the output state that we have is an A1 plus B0. This is the simplest quantum circuit that one can draw using the quantum NOT gate. So using this example, it should be clear now that quantum gates in general are matrices. They are 2 by 2 matrices, but they can't be any arbitrary 2 by 2 matrix. They have to be matrices that preserve norm, right? And so what are these matrices? They are unitary matrices. So any 2 by 2 unitary matrix is a valid quantum gate on a single qubit, right? So these are what are called single qubit gates. And again, you see the departure from the classical case. In the classical case, while the NOT gate is reversible, what do I mean by reversible? That I can map sort of uniquely from the output back to the input. If my output is 1, I know that my input should have been 0, and if my output is 0, I know that the input should have been 1. But if you look at any of the 2 qubit gates, in the 2-bit gates in the classical case, like the AND gate, the OR gate, etc., then they are not reversible. But quantum gates, because they are unitary matrices, are always reversible, right? So let's focus on a few more single qubit gates, right? Again, classically, there's just one single bit gate that you can think of, namely the NOT gate, which maps 0 to 1 and 1 to 0. But quantum phase space is much richer, as we just saw, right? The phase space of a qubit is much richer. So you can actually think of other interesting gates just on single qubits. So here's an example. We looked at the sigma x matrix in the previous slide, and that gave us a quantum NOT gate. What does a sigma z gate do? We call that this is the matrix for the sigma z operator, and of course recall that we have chosen ket 0 and ket 1 to be eigenstates of the sigma z operator. So of course ket 0 is the +1 eigenstate and ket 1 is the -1 eigenstate. So this is how the sigma z gate would act on the ket 0 and the ket 1. But what operation is this really doing? Because it's doing nothing to ket 0, and for ket 1 it seems to be adding a minus sign, which is like an overall phase, right? Because of course this is e to the I pi, so this is like an overall phase. So is this gate really doing anything non-trivial? Well, yes, it does if you think of an arbitrary qubit state. So think of an arbitrary superposition of 0 and 1, A0 plus B1. Let's say that we have fixed A and B to be cosine and sine like before. So initially, the relative phase between the 0 and the 1 was actually a 0. That's what this plus sign is telling you. But now when sigma z acts on it, it does nothing to ket 0, but it adds a minus sign in front of ket 1. So what it does is it modifies this relative phase to something else. What was originally 0 now becomes e to the I pi. So the relative phase becomes pi, and you have this additional, and now you have a minus sign here. So this is why the sigma z matrix is called a quantum phase gate. It modifies the relative phase in a superposition. One can of course now go ahead and construct many more such quantum gates which do not actually have a classical analog. There's no classical analog of a phase gate, right? One simple set of gates that you can already think about, sigma x, sigma z have been mentioned. So next you can think about sigma y. Of course, it's a good exercise to check that these are all unitary matrices. They satisfy the property that u times u dagger is equal to u dagger times u's identity. Also, maybe it's useful for you to work out how does sigma y transform a single qubit state. I'm just going to mention one more interesting and useful quantum gate out here, single qubit gate. This is what is called a Hadamard gate. It is represented by this 2 by 2 matrix, 1, 1, 1, minus 1 with an overall factor of 1 over square root 2 outside. Why is this an interesting matrix? This is actually a matrix that you should have already encountered if you had worked out the homework problems, if you had worked out the tutorials, because this is a matrix that actually transforms from the sigma z basis to the sigma x basis and vice versa. So H acting on ket 0 gives you Sx plus, which is the plus eigenstate of the sigma x operator. H acting on ket 1, which is the minus half eigenstate of sigma z, takes you to the minus half eigenstate of the sigma x operator. So this is a basis transformation unitary. It's a very useful quantum gate. You can also think about what is H inverse. Remember, for unitary matrices, the inverse is the same as the complex conjugate transpose or the dagger operation. You can check that in fact in this case H inverse is the same as H, and obviously what H inverse should do is to map you back from sigma x eigenstates to the sigma z eigenstates. Okay, so these were all single qubit gates, but what about operations on multiple qubits? Surely we can't do quantum computing just using a single qubit state. We will need to use multiple qubits. So how do we think about multi-qubit gates? So here's an example of that. So the first thing we should do is to understand the 2-qubit space. So let's just work out a simple 2-qubit gate. Recall that we can write down the basis for a 2-qubit space using a set of 4 vectors. One easy way to think about it is to make a comparison with the classical case. If I had 2 bits, what are the possible set of values that these 2 classical bits can take? They can take one of 4 possible values, 0, 0, 0, 1, 1, 0, 1, 1. So I can label my 4 orthogonal states using 0, 0, 0, 1, 1, 0, 1, 1. So in a way it's sort of clear that I should have a 4-dimensional complex linear vector space to represent the state of 2 qubits, right? By making this analogy with the classical bit. I'm just going to mention here an equivalent representation of this. There are 2 qubits out here. So in the computing language, you think of these as 2 registers, right? So I can explicitly write this down as a ket 0, just to show you that the first register is in state 0, second register is in state 0, ket 0, ket 1, first register is in state 0, second register in state 1, and so on. So this notation is just explicitly writing, separating out the state of the individual qubits. It's just a different notation, writing the same orthonormal basis. So what kind of objects would transform states of 2 qubits, would map from one state of one 2-qubit state to another 2-qubit state? Well, there's a 4-dimensional space, so we will need 4 by 4 matrices. Specifically, we will need 4 by 4 unitary matrices. So here's an example of such a 4 by 4 unitary matrix. I'm first going to describe it using a quantum circuit. So this gate is called a controlled NOT gate. And now remember, I have two qubit I have two registers because I'm working in a 2-qubit space. So here I have two wires, the first wire representing the first register, second wire representing the second register. This is the symbol of the CNOT gate, right? And you will understand this symbol very soon. I have my input state is now a 2-qubit state, right? The first qubit I think of as a control qubit, and the second qubit I think of as a target qubit. The X and Y are just placeholders for the bit values 0 or 1. What does the CNOT gate do in the circuit representation? It does nothing to the control qubit. The control qubit is preserved as it is. But the second qubit or the second register or the target register is modified. And how is it modified? It is modified depending on the value of the control bit using a classical operation, a classical Boolean operation. What is this operation which is denoted by this sum notation? Basically, it's the XOR operation, right? So this sum out here represents the XOR operation. Recall that the XOR classical gate has this kind of a truth table. It's basically addition modulo 2. So 0, 0, 0 XOR 0 is 0, 1 XOR 0 is 1, etc. But the key thing to remember is that 1 XOR 1 gives me 0 because it's addition modulo 2. So now if you use this truth table to work out what happens to different input states, you will notice that this target qubit is basically flipped only when the control qubit is 1. And that's why this is like a NOT gate. It's like a NOT gate on the target qubit, but controlled by the first qubit, and that's why it's called a controlled NOT gate. So one can explicitly write out a truth table for the CNOT gate like this. If the input state is 0, 0, the output is 0, 0 because 0 XOR 0 is 0. If the input is 0, 1, the output is again 0, 1 because the control is 0. The target is just 0 XOR 1, which is 1. Now when the control is 1 and the target is 0, the first qubit or the control qubit is still 1. But now you see the target, which was originally 0, has become 1 because of the XOR operation. So the target has now gotten flipped here. Similarly, when the control is 1 and target is 1, after the action of the CNOT gate, the control remains 1, but the target has again gotten flipped because 1 XOR 1 is 0. So only in the case that the control qubit is 1, you see that the target qubit has been flipped. The second qubit has been flipped. So this is a controlled NOT gate. One can also write down a matrix representation for this because I started by saying that this kind of an operation is realized using a 4 by 4 unitary matrix. Remember, these are basis vectors for me. So in this basis, what does the control NOT operation look like? Well, it looks like this kind of a 4 by 4 matrix. Remember that the first two basis states, which is 0, 0, 0, 1, nothing happens basically to either qubit, right? So you can make a kind of correspondence like this. The first two basis states are 0, 0, 0, 1, nothing happens. The second two basis states are 1, 0, 1, 1, but now you notice that they have gotten flipped. The 1, 0 has been mapped to a 1, 1 and the 1, 1 has been mapped to a 1, 0. So for the second pair of basis states, this essentially acts like a sigma X operation, right? Remember that this is nothing but your NOT gate, so hence the name controlled NOT gate. This is a very important and useful quantum gate. One of the things that you notice is that this gate actually, in a sense, introduces some correlation between the two qubits, right? Originally, it was just some qubit X and qubit Y, right? But the output now, the state of the second qubit depends on what the original state of the first qubit was. So this is a gate that has introduced some correlation, and we'll explore this idea a bit more in the next slide. A final thing to note is the idea of universal gates. Classically, once I have my 2-bit gates like AND or XOR, etc., you know that you can talk about universal gates. The NAND operation, is universal, and so on. So similarly, in the quantum case, once you have this C0 gate, and once you have the sort of single qubit gates that I described in the previous slide, then you can achieve universality. That is, any quantum gate, multi-qubit quantum gate, can be represented in terms of just single qubit gates and the C0. And that's why the C0 is an important quantum gate. So here's a simple quantum circuit, right? I just wanted to show you an example of a quantum circuit. And this is a circuit that does something interesting from a physical point of view as well. So what does this circuit comprise of? It's a 2-qubit circuit. The 2 input registers have been set to 0. I start with the Hadamard gate, the H gate, which I just described 2 slides ago. Remember, that's the matrix 1, 1, 1, minus 1. Followed by the C0 gate, which we just described in the previous slide. So what is the output state now? So how do we work out the output state? First, note that the Hadamard acts only on the first qubit. And remember, this takes the sigma z eigenstates to the sigma x eigenstates. So specifically, it maps 0 to Sx plus. And what is Sx plus? That's a superposition of 0 and 1, 0 plus 1 by root 2. So we've gone from just 0, 0 to Sx plus 0, which is nothing but 0 plus 1 by root 2, 0. So the first register has now been thrown into a superposition. I can expand this state out and write it as 0, 0 plus 1, 0. Note how I'm going back and forth between the two notations, where I explicitly separate out the 2 qubits here, and I can also write out the label within a single ket, right? And it doesn't matter here. Okay, now how does the C0 act on this kind of a state, where the 2 qubits are now in a superposition of 0, 0 and 1, 0? Well, the C0 should do nothing to the first vector in the superposition. Why? Because the control is 0, so it should do nothing to the target. So 0, 0 just gets mapped to 0, 0. But the second vector in the superposition, the 1, 0 state, remember, is modified by the C0. So the 1, 0 should become a 1, 1, because now the target gets flipped since the control is 1. And now you see what happens is that the output state is of this form. It's a 0, 0 plus 1, 1 by root 2, and this is an example of what is called an entangled state. Why is this an entangled state? Because this is now a state which has some correlations, right? And how do we understand this correlation? Basically, if you look at the two states, the two vectors in this superposition, they are of the form 0, 0, 1, 1, which means if I do a sigma z measurement on the first qubit and I get an outcome 0, I have to get an outcome 0 if I measure sigma z on the second qubit as well. If I measure sigma z on the first qubit and I get an outcome 1, then I must get an outcome 1 in the second qubit as well. Which means if the first qubit has a spin plus half, so must the second qubit. If my first qubit has a spin minus half, then so must the second qubit. What this tells me is that the spin outcomes of the sigma z measurement are correlated between the first and the second qubit in the state. So this is an example, a simplest example and a very crucial example of an entangled quantum state. Another way to think about this is that this is now a superposition only of 0, 0 and 1, 1. There are two other states, two other basis states here, the 1, 0 and the 0, 1, and they do not figure in the superposition. If I had all those states, then it wouldn't be an entangled state, but I have only the correlated states 0, 0 and 1, 1. So this is why the C0 is important, because essentially what it has done, it has taken two individual single qubit registers and it has transformed them through the Hadamard into such an entangled state. So this was just to give you a kind of glimpse of what quantum gates are capable of and what kind of quantum circuits one can visualize